We begin with number systems. Early mathematics consisted of what we would now call positive integers, though at the time there was no reason to call them positive. They were simply numbers. With them, people could count objects, trade goods, build structures, and even do basic algebra and geometry. Fractions existed as well. Let's take a look at what some of these early number systems actually looked like and how the mathematics worked. In this example, the blue square represents 1 and the green triangle represents 10. So if we have 5 squares and 2 triangles, that represents the number 25. The key difficulty with writing large numbers in these systems is that they did not use place value. Instead of using the same symbol in different positions, they had to use entirely different symbols to represent different quantities. In our modern place value system, we reuse the same symbols. A 2 can mean 2, 20, or 200 depending on where it appears. The position itself carries meaning, like that's what makes it a place value system. But in these older systems, position didn't matter. A symbol meant the same thing no matter where it appeared. So having a 2 in one spot versus another had no special significance. To represent different magnitudes, entirely new symbols were required. Each symbol carried its own fixed value, independent of position. Now let's consider addition. On the right, we have 25 plus 7. Using symbols, we combine everything below the line, all the squares and triangles together. Once grouped, we notice that 10 squares can be exchanged for 1 triangle. After making that conversion, we're left with 3 triangles and 2 squares, which corresponds to 32. Even in this small example, we can already see how cumbersome and inefficient this process is. And as numbers grow larger, the difficulty increases rapidly. This is why the development of a place value system was such a major breakthrough in mathematics. At first, place value systems existed without something like 0 to occupy a position when there was nothing there. Instead of writing a symbol, mathematicians would often leave a gap or empty space between places. But this gap was inconsistent. Some people would interpret it as an empty position, while others wouldn't notice it at all. So if someone tried to write the number 102 by writing 1, space 2, some would read it as 12, and others as 102. This made calculation unreliable and communication unclear. It hinted that something important was still missing, a placeholder for nothing. This is where the story of 0 begins. At first, 0 wasn't really a number. It was just a placeholder, but that alone was revolutionary. Suddenly, large numbers became easy to write, interpret, and calculate with. That problem was finally solved. But soon, another problem appeared. What if a merchant spends more than they earn in a month? What does something like 5 minus 8 mean? At first, there was no number to represent the answer algebraically. This hinted that the number system was still incomplete. To solve these problems, mathematicians introduced negative numbers, extending the number line in the opposite direction. Now things are really coming together. Positive numbers, negative numbers, and a placeholder 0. But consider one more case. What if the merchant spends exactly what they earn? That gives us 8 minus 8. The result corresponds to nothing, but there still wasn't a number that behaved algebraically as that result. This changes in the 7th century, when the Indian mathematician Brahmagupta introduces 0 as a number and defines arithmetic rules for it. For example, 8 minus 8 equals 0. 8 plus 0 equals 8. 0 becomes a true mathematical object. It's worth noting that the broader intellectual context of Indian mathematics, including ideas related to emptiness and absence, likely helped make this concept possible. The word Brahmagupta used, shunya, a Sanskrit term with deep roots in Indian philosophical and religious thought, means void or emptiness. There were even attempts to define division by 0, but these ultimately failed. In modern algebra, division means multiplying by a multiplicative inverse. A number's multiplicative inverse is the number which, when multiplied by the original number, gives 1. For example, 5 times 1/5 equals 1, 12 times 1/12 equals 1, negative 7 times negative, 1/7 equals 1. 1/8 times 8 equals 1. This idea allows us to reinterpret division. For instance, consider 10 divided by 5. 10 divided by 5 is equal to 10 times 1/5, which is equal to 5 plus 5 times 1/5, which is equal to 5 times 1/5 plus 5 times 1/5, which is equal to 1 plus 1, which equals our final answer of 2. So division can be expressed entirely in terms of multiplication and inverses. Now return to the question of dividing by 0. To divide by 0, 0 would need a multiplicative inverse, meaning there must exist some number which, when multiplied by 0, equals 1. However, that is impossible because 0 times any number is 0. This is ultimately why division by 0 remains undefined. At this point, mathematics is powerful. Algebra and geometry flourished, but mostly as separate subjects, for centuries. Then, in the 1600s, something remarkable happens. René Descartes introduces the Cartesian plane. Geometry and algebra merge. Points become numbers. Curves become equations. Equations become curves. This single idea changes mathematics. To see why, let's consider a mathematical idea that had been around for thousands of years: steepness or inclination. We all encounter steepness in daily life, especially when we start walking uphill and suddenly feel ourselves working harder. But beyond just experiencing it, mathematicians had long tried to describe steepness. For example, the ancient Egyptians used a concept called seked, which measured how much horizontal run corresponded to a unit of vertical rise. It worked well for practical tasks like building pyramids, but it was limited in scope and context. For most of history, the calculation of inclination had never been fully formalized mathematically. That begins to change when Descartes introduces the Cartesian plane. Suddenly, steepness becomes something we can calculate, compare, and represent algebraically. And with that formalization, a whole new world of mathematical questions becomes available. Around this time, the modern term slope comes into use. Prior to the Cartesian plane, slopes were really only treated for straight lines. Talking about the slope of a curved line didn't lead very far because slope itself wasn't yet understood as a generalizable mathematical object. But once slope is formalized on the Cartesian plane, it takes on new meaning. Now we can talk about slopes of curves, not just straight lines. And immediately, a new problem appears: instantaneous slope. To see how this problem emerges, let's begin with the slope of a straight line. The change in y is represented by the blue segment, and the change in x is represented by the red segment. For this line, the change in y is 8 and the change in x is 4. Since 8 divided by 4 equals 2, the slope of the line is 2. Now consider the next line. This one is less steep, so we expect a smaller slope. The change in y is 4 and the change in x is 4. Since 4 divided by 4 equals 1, the slope of this line is 1. But what happens if we want to find the slope of a curved line? Notice that some parts of the curve are steeper than others. The steepness, the slope, changes continuously as we move along the curve. So we cannot calculate the slope of a curved line the same way we did for straight lines. Instead, we would need to calculate the slope at a particular point. At first, that idea seems reasonable, but as soon as we apply the definition of slope, the difficulty becomes clear. Slope is defined as change in y divided by change in x. But at a single point, there is no change in x or y. The 2 points collapse into 1 and the formula collapses with them. We get something that looks like 0 divided by 0. This problem is not a technical annoyance. It's a fundamental limitation of existing math. Around the same time, independently, Isaac Newton and Gottfried Wilhelm Leibniz attempted to solve this problem in the mid-17th century. They did so by asking what value an expression approaches, rather than what value it has at an exact point. To understand what this means, consider the following function. The function shown here is the blue curve, including the blue dot. We can see that when x equals 2, y equals 6, which means the function equals 6 at x equals 2. But the value that the function approaches as x gets closer to 2 is 3, represented by the open white circle. Now consider a function that is undefined at some x value. In this example, the function is undefined at x equals 2, since no part of the function exists there. And yet, the function still approaches the value 3 as x approaches 2. Therefore, by looking at what happens to a value as we approach 0, without ever evaluating it at 0, we can define the derivative. The instantaneous slope exists after all, and with that breakthrough, a new branch of mathematics is born. Calculus, the mathematics of change. Calculus goes far beyond simply giving us the slope of a function at a specific point. It provides tools for understanding any situation involving change. For example, we use it to find areas under curves, to move from position functions to velocity functions, to model population growth, and to analyze systems that evolve over time. In fact, without calculus, modern space travel as we know it would not be possible.